Okay, we're gonna see where all the equations of the stresses and strains that we use come from. This is a good reminder to understand why we calculate things like I and J, and especially for the shearing stresses, Q and T, and what those means. Those terms mean. So we'll start with the first one. If I have a rod, whatever kind of structure, it doesn't matter if it's tubular or circular, it can be anything, and it's subjected to a compressive force. We define the stress as that force, that load P over area. In reality, when we're close to these surfaces, there's going to be a higher stress here, and as I move down and down and down, at some point those are going to be actually distributed. So this is like the average stress, but the farther away I move from the sides, from the top and the bottom layer or surface, this is going to become true, and somewhere in the middle it would definitely be P over area to calculate that stress. So that's the normal stress, and we know that the property that relates the stresses and strains and the elastic range is what we call the elastic modulus. So I know that E is sigma over epsilon, which is defined as our strain. And the strain is just going to be, the engineering strain is going to be L minus L sub 0 over L sub 0. So the change in length over the original length. As you've heard before, and I've mentioned in class, there's the real strain, which would be just the integral of the change of length over length, and this is going to give you a natural logarithm, but we're not interested in that. We're going to use the engineering strain. And so the delta L we usually refer to as a delta, Greek letter, over L sub 0. And this we just call L because that's probably the length that we're given for all of the structures that we deal with. So if delta over L is equal to epsilon, and epsilon is equal to sigma over E, sigma over elastic modulus, and the elastic modulus is P over A times E here in the denominator. From here, I can identify that the delta is PL over AE, and that's the other equation that we use a lot. So the strains for compression or tension are given by this equation, and the stresses are given by this equation. Okay, so axial or normal stresses due to compression and tension, and if they're under compression, we define these as negative stresses, and if this is under tension, we define the stress as a positive stress. Okay. Then we moved on to torsion. So if I have a shaft, a rod, whatever, that is subjected to a torque, which is nothing more than a moment in the axial direction around the axis of the rod or the structure, we define two things. So due to that torsion, there's going to be an angle of twist. I'm going to do this a little bit. I'm going to do two different drawings. If this dotted line originally was right here, when I apply the torque T, this is going to move. Obviously, I'm exaggerating how much that moves. Somewhere to here. Okay, and we call that the angle gamma, because that is the same gamma that we would see under a small element under shear stress. Okay, so if I apply a tau to this little element, what I would see is that it deforms like this, and the angle gamma is defined as this, or well, yeah, you would say gamma over 2 if you're moving all of the sides, but here if I'm assuming that this how the element is deforming, I would just have an angle gamma here. So an original element that I had here, tiny one, after the deformation, it would be somewhere here. So that's why this angle here of rotation between these two dashed lines would be also gamma. Okay, and the other one that I'm interested in is this angle, theta, that I call the angle of angle of twist, angle of rotation. So what I know is that this ds from A to B, that arc ds, can either be calculated as sigma times the radius of the cylinder or the rod, or the length of the rod, L, times the angle gamma. So from this is where I'm going to get my angle of twist theta, which will be L times gamma over R. And we'll use that as soon as I know how to find this gamma. So I'm going to use this equation to find my angle of twist. And I can also solve for gamma in that, from that same equation, just to see that this gamma is going to be linear. Going to have a linear relationship to gamma max, depending on where I'm looking at the strain. So for gamma, I would have R theta over L, and what that means is that the gamma that I would be looking at depends on what radius I'm using. So the gamma would be smaller if the radius that I'm looking for is somewhere over here in the middle and not on the surface of the rod. So basically I have a gamma max where the maximum R is equal to the maximum radius, which we usually call C, sigma over L. And if we relate these two, all we see is that gamma is gamma max. It's just a fraction of gamma max, which is R over C, where R can be anything between 0 and C. Okay, so a linear relationship between those two. Now if I look at the stresses, so just another drawing of this. If I'm looking at the stresses here from the center, for any given R, I'm going to find a small stress element that will have, due to that torsion, a force in this direction. And so I could calculate the total T as the integral of R, whatever R I'm using to find that element. It could be a smaller R closer to R, or a higher R closer to the surface, times dF. And because of all of these stress elements, any of those that I'm getting will be under shear. So there's a higher force here than here, so there's going to be a shear for them. I can write this dF as my stress, which in this case would be a shearing stress, times the area. Okay, that would be stress times the area will give me the force. Now from this relationship, I can say the same thing about tau. If I multiply this by my shearing modulus, just like I did, like if I multiply E times epsilon, I get the stress. I can do the same thing, but not the elastic modulus, but with the shearing modulus to get not the normal stress, but the shearing stress. And again, my strain would not be the linear one, but my strain gamma. So G times gamma would be a tau. G times sigma gamma max would be tau max. And I would still be multiplying by a fraction of R over C, where C is the maximum radius. And again, this is just a linear relationship. So if I use that definition of torque with the integral, and the relationship between tau and tau max, I can write from here, I can see that T is equal to R tau dA, and tau would depend on the radius. The shearing stress is not the same at different radial directions, but different radial locations. But what I know is that T can be written as R over C times tau max, which is what I just wrote here. Okay, so instead of tau, I do tau max R over C, the area, times another radius that I had outside the parentheses. And since tau max on the surface is constant and C is just the maximum radius of the cylinder, which is also constant, I can just write this as R over C integral of, tau max over C times R squared dA. And that would be the torque. And this is what we call the second polar moment. Second moment of area in the polar coordinates. And that's what we define as J. Okay? And so usually, yeah, we just use find what the J is of a circle or of a hollow cylinder, but it comes from this integral. So let's do it pretty quickly. The D area, so this is a double integral, and my D area, so I'm going to do a circle here, and at some point dr, I'm going to have a tiny area element, and if I blow this up, you would see something like this, where this angle from the center is d theta, and then this length is just the smallest fraction of a radius, so that's dr. And so if this is located as a distance of r, if I multiply r times d theta, I would have r, the length of this arc, which again, if this angle is small enough, we can assume that this is just a square. So the area of this small area would be, the area of this small square would be r d theta times dr, just as if it was an actual square. So that d area is r d theta dr, or r dr d theta, and I'm integrating r squared. And I'm going to do it for all the angles. So my first integral with respect to the theta would be from 0 to 2 pi if I'm doing radians, and then for the radius it would be from 0 to the actual radius, like C for example, or just capital R, whatever. This distance would be capital R, 0 to R. And so this is basically just from 0 to 2 pi 0 to R of R cubed dr d theta. So this first integral would just be r to the 4th over 4, evaluated at capital R and 0. So at 0 it's going to be 0, at capital R it would be this, and this would still be inside my second integral. And then from 0 to 2 theta of d theta would just be theta evaluated at 2 pi and 0. So r to the 4th over 4 times 2 pi is what J would be, and this, just by organizing this, would be pi over 2 r to the 4th. And this is what we've been using, either pi over 2 r to the 4th, or if r is half of a diameter, 2 to the 4 would be 2, 4, 8, 16, d to the 4th over 16, which is equal to pi over 32 d to the 4th. And that's why we use this equation. Okay, and you can do the same with the hollow one. So if it's hollow, it would be not from 0 to r, but from like r inner radius to outer radius, and all you end up with is a subtraction here. So r to the 4th minus r to the 4th, outer minus inner, and basically you end up with the same thing. The outer to the 4th minus the inner to the 4th. We've used that before, and you've used it probably a lot of times too. That's where the J comes from. So going back to here, where I've defined this as my J, I know that the torque is equal to tau max over C times J. And this is exactly what we want. We want the tau max, shearing stress from the torsion, and that's equal to 2 TC over J. And that's the other equation that we use over. Okay. We are always interested in the maximum, which occurs at C, which is radius of the shaft or the rod, and that's because the stress distribution is going to be 0 at the center, and because of the linear equations that we've shown already a lot, it's going to be highest at the surface. So we're always interested in this tau max. We don't want to know if if at 1/3 of the radius it's 1/3 of the tau max, because we're not going to compare that to any of the properties of the materials. We know that we're comparing the maximum stresses anyways. That's why we use this equation. And so going back to this relationship that I had with the angle gamma, and knowing that gamma max was C theta over L, I can write that sigma, if I multiply this by G here, I would get a tau max. So basically C theta over L times G would be my tau max, but I already know what tau max is. I'm going to do that separately. So if my tau max is equal to C theta over L times G, and my tau max is TC over J, the C's go away, and what I'm left with for theta is T times L. L goes to multiply, and then G to the denominator over JG. Okay, and this is what we call the angle of twist. So far we have normal stresses, P over A, and an associated deflection or changing length, PL over AE, and tau, which I know it's the tau max TC over J, and an angle of twist, TL over JG. Okay. Now there's bending, which, as I explained, so this is normal, oppression, tension. This is shearing, torsion, and I'm gonna have another that gives me normal stresses that comes from bending. Okay, so when I have a beam and it's being subjected to some moments, bending moments, there's gonna be one layer that is not gonna deform. So if that was originally L, I would still find something that was not compressed or stretched, but because of the moment, this length, for example AB, would no longer be the same length as AB or CD. It would be much shorter, so it's under compression. But the other side here, in this example at the bottom, would be stretched. Okay, and that's what we call that's the stresses that we're interested in, either the top or the bottom one, because that's where the largest normal stresses are found. So let's do that for bending. So basically I'm just gonna redo this so that I can show some of the variables. So I'm obviously exaggerating the radius of curvature to make it a super small one, but basically what I said before is that the radius of curvature of this beam will allow me to reach that layer, that plane where the beam is not being stretched or compressed, and that's what we call the neutral axis. Okay, if I go up for a positive moment like this, I would find compression. If I go down, I would find tension. And so the neutral axis is going to be my point of reference. If I move from my neutral axis up to a distance of y, and it doesn't need to be to the top surface, it can be anywhere. In this case, we'll do it to the top surface. This distance right here would be the radius of curvature minus y. Okay. What I can define from this is the strain. So if I have theta, doesn't matter, just the theta. I can define the strain on this plane, on the top plane, and that would just be using my strain definition, L over L sub 0 over minus L sub 0 over L sub 0. L would just be this length L, which is rho times theta. Sorry, that's the original length, so minus rho theta over rho theta, that's L sub 0. And the new one, the compressed one here, would be rho minus y, which is this length from here to here. So this radius times d theta would give me this arc, which is the length L, times theta. Rho minus y times theta would be that length of the arc. And so theta goes away, and rho minus rho 0, I only end up with minus y over rho, and that's defined as the strain. And so again, just like I did before, by defining the maximum and the minimum, this E, if y would be c, so going all the way up or going all the way down, so where c is just my y max, I can define that E max times a fraction y over c, so just a fraction of that, whatever y over the maximum y, multiplied by my E max, would be equal to my epsilon for the deformation. So basically all I'm saying here is E max would be not for any y, but c over rho. So if I compare this with a c and this with a y, I end up with this relationship right here. Okay, and again, if I multiply by the elastic modulus on the left and the right, I would get that sigma max is equal, or times y over c is equal to any sigma, right? A fraction y over c. So this just means that these stresses right here are also linear. The farther away I move from the neutral axis, the higher they are, but in a linear fashion, as long as obviously I'm in the linear phases of my deformation. And I'm going to use this to find the stress in terms of the moment. So if I look at a beam, if I have any shape of beam, and let's say this is already a cut, I will find my neutral axis. If I move a distance of y in the y direction, I would find a tiny element of stress here. And if I'm looking at this from the left, from this view, let's say this is my x-axis and this is my y-axis, what I would see is that on the neutral axis there's no stresses, but again, as I move further away from the neutral axis, up or down, and my sigma would increase up to reaching the sigma max. So it would look something like this in a linear fashion, and then if I go down, it would be under tension, so the vectors would go in the opposite direction. So basically what I'm saying here is that there's going to be a force dF going in that direction, and if I multiply the distance y times the dF, I would get, and integrate all of those, I would get my moment. Okay, so distance times force, I would get a moment in that direction, and my dF can be written as sigma times the area. Okay, again, if I multiply the stress times the area, I would get my force. And this is the sigma from the bending that we're interested in. So this sigma is just this one that I can define as just a fraction of the maximum sigma here for any y I get. And if I do the integral, I would get the maximum moment. So let's do that. What I have is m equal to, from this, y times this all had a minus from the minus y over from the minus c over rho from the Emax, so minus y over c times sigma max. So all I'm replacing here is sigma in terms of sigma max, the area, and what I would get, since C is the maximum y, and that's constant, and the sigma max is whatever this value is, and that is also constant, those can come out of the integral. So I would have sigma max over C times the integral, or negative, times the integral of y squared dA. And so this is in the normal coordinates, it's not radial, so I don't call it the polar second moment of area, but just the second moment of area. Second moment of area. And if that's just called I can solve for my sigma max, which would be minus m times C divided by I. Okay, and if I don't want the maximum, if I just want to find the sigma at some point between the neutral axis and the maximum, I can just use this relationship here again. So if I don't want the maximum but just some sigma, it would just be y over C times that. So if I multiply, sigma would just be C y over C times my sigma max, y over C times my sigma max. C's go away, and this is just minus my over I. Okay, so going back to all the stresses that I have so far, I have my normal stresses due to normal loads, shearing stresses due to torsion and normal bending. I would have a sigma equals to minus m y over I. Now, something that I kind of skipped here, I realized I made a small mistake. This is still positive here, and this is still negative here, but the reason these moments are negative, so the integral, as I defined it first, is that for this positive moment, it makes this smile, and that's how I define positive moments. The forces here for a positive y would go in this direction, so that would be causing a negative moment, and so that's why we add the negative here. And we can also work on the second moment of area, like we did for the polar second moment of area. And so, well, it's going to depend, and we use things like the parallel axis theorem to get the total moment, what we call the total moment of inertia, that we should actually be called the second moment of area because we're not dealing with the mass or anything. But let's do just like the one that we use the most, which would be a rectangle of base B and height h. If I'm located at the neutral axis, this integral would be from 0 to b, so this d area would just be dx dy, dx dy. Dx would go from 0 to b, and dy would go from minus h over 2 to h over 2. Again, if my point of reference is my neutral axis, which is right here at the center. Okay, if I'm doing it from the bottom, it would be from 0 to h over 2, but you can figure that out later. And so the second moment is just y squared, the area. So if I do the outer one first, it would just be b minus 0 times the other integral over 2h over 2 y squared dy, and this would be y to the third over 3 evaluated at h over 2 and then minus h over 2, and still multiplying by b. So h cubed over 2 cubed is an 8, h cubed 8, minus h cubed over 8 times b, and times the 3 that I had here, 3 and 3. So it was h over 3, h halves to the third over 3, and that halves to the third becomes an 8, but the 3 is still there. So this ends up being 24, 2 over 24, or just 1 over 12 bh cubed. And that's what we use, for example, for a rectangle. But you can basically do the same thing for a circle or any shape, a triangle or whatever, if you have a triangular beam for some reason. Okay, and so we had the stress, but we don't have the strain, or what we're interested in bending, which would be the deflection of the beam. So let's do that. From this relationship right here, where the strain was defined as minus y over rho, from this analysis here. So if strain is equal to minus y over rho, and rho being the radius of curvature, I know that the radius of curvature would be minus y over the strain. Now from math, I know that the radius of curvature, so I'm not going to do this whole process, the calculus part of this, but it can be defined as y double prime over 1 plus y prime squared to the 3/2. And what we are going to see, where y is just like the function y of x, so the first derivative and the second derivative, is that the first derivative where y is representing, so if I have a beam and y is just describing this curve, so that I have the radius of curvature, y would be the actual deflection of the beam. It would be the function that would give me a picture. If I take a picture of the deflected beam, y would be that function. Okay, so y prime, which would be the slope of how the beam is looking, we're going to assume that in most of the mechanical engineering and engineering in general, structural engineering, those angles are very, very small. So something that is very, very small squared plus 1 would just be like completely negligible, almost to 0. So this would be just 1 to the 3/2, which is still 1. So basically what I'm saying is that the radius of curvature for this applications is just the second derivative of y with respect to x. Okay, so this from a mechanics of materials here a perspective, and then this from math. So if I know that epsilon is also, so sigma is equal to E times epsilon, so epsilon is equal to sigma over E, this would be minus y over epsilon, which is sigma over E. Alright, and I just found sigma. I know that my stresses are minus my over I. So I m y with the minus, this is the stress here. So y and y go away, minus and minus become a plus. And so my radius of curvature is E I over m. And I know that the radius of curvature will give me the second derivative of that deflection with respect to x. Okay, and this is what we use, and this is the reason we can either start with the loads and integrate once to get v, and then integrate twice to get m, and then once we have m, this is going to be the second derivative, so we integrate again. We're going to get a c1 to get the slope, dy dx, which is just the slope of x, and then integrate once more to get y of x, which is the actual deflection. And so this is the reason why we do, if we have a beam with distributed loads somewhere, and then punctual loads somewhere else, and then there's probably a reaction and maybe an external moment, if we can write a function w of x where I get all of these, and using the singularity functions, I can integrate this once to get v of x, and obviously there's a negative right there, and integrate again to get the moment of x, and you have the minus here, and then integrate again to get the theta of x, with integrating here the 1 over EI. So the derivative is EI over m, so if I integrate m, I would get the slope if I divide by E and I, and then integrate once more to get the actual deflection. Okay, something like this. This is just so that you remember what we used to do. And every time we do this integral, we have a constant. So the constants between the loads and the shear would be the external shears. The constants that come by integrating the shear to get the moments would be the external moments, even the reaction ones too. And for the slope and the y's, the actual deflection, we're going to get a C1 and C2. And for those C1s and C2, and C1x plus C2, what we did was looking at the boundary conditions. So I would know, for example, in this case, that the slope here at the wall would always be 0. So you would have something like theta of whatever L is 0, and then another one would be that the deflection here is not going up or down. So y of x with x equal to L, y of L would also be 0. And use these boundary conditions to solve in most cases a system of 2 equations and 2 variables. In some others, if I don't know, if the wall was at the left side or something and this is just 0, you would get that C2 is 0 right away, because you would know that the deflection at 0 is 0. So all of these terms would be 0, and then C2 has to be equal to 0. That's how you find the constant. Okay, so we use this. We use the fact that the radius of curvature is the second derivative of y with respect to x. And then the last one is shearing, the transverse shearing, which in most cases is caused by some loads that are also causing bending. So these two are kind of related. And so we need a shearing stress due to those loads that also cause the bending. Now that one is really important because that's where I've noticed where most of the questions are. What is Q and what is T, or why T is what it is and whatever. So we'll work on that. So let's say I have, again, just a beam like I drew it before with some cross-section area like a trapezoid. And what I'm going to take from this is, so if I look at this from the side, I'm going to do a cut here. So I'm going to get a small cut of this beam. And if I look at it from the side, it would just be something like this. But also I'm going to cut it somewhere above the neutral axis. Could be a neutral axis, it doesn't matter. I'm just going to cut it from here on that layer, that plane. And so this from the side would just look like this. I'm going to take this one, this piece of beam. So basically this thing. And actually I can just do another drawing here showing what it would look like without the beam, without the portion of the beam that I just took out. It would be something like this. And so the shearing force is going to be due to the force that affects this shaded area. Okay, so that area would just be this if I'm looking at it from the side. And what I'm going to find, if I blow this up to that element, this beam can be subjected to, I don't know, some distributed loads and some punctual loads, whatever. What I'm going to find is that, yes, I would have that distributed load here, W. I'm going to call it this just C and D. And because of the bending that is caused in this situation, it doesn't matter what the direction of the forces are, the equation is going to be the same. What I said before is that from the neutral axis, there's not going to be any normal stresses due to bending. But as I move away from the neutral axis, I'm going to find some stresses. So in that cut that I took out, I would see something like this. That is linear. Just doesn't start from 0, but it is linear. Okay, the farther away I move from the neutral axis, that would be somewhere around here. So let's say the neutral axis is somewhere around here. I would see something like that. And what I'm saying is this shaded area, this line right here, is going to be subjected to a force. That obviously, if I divide that force over the area, would give me the shearing stress. So that's why we're doing this cut. And that force is usually referred to as a delta H. Okay, so I don't really mind, like there's going to be a VC and a VD, and again the directions, I don't know what the directions are going to be for those vectors, but I know that there's going to be some shearing forces as well in that direction. If I do the sum of forces in the x direction here, assuming this is the x axis, what I'm going to find is that I'm going to have sigma at C, that bending moment at C, and the bending moment at D is going to be slightly different. I move from C to D, the moments are going to be different, and therefore the sigmas are going to be different. So times the area and integral, that would be positive, and then at D would be negative, sigma D the area, and then this force, that is what I'm interested in, because if I divide it by this shaded area right here, I would get the shearing stress, plus delta H has to be equal to 0, because this element is not moving to the right or to the left. Okay, so basically delta H is equal to sigma D dA minus sigma C dA, and I know that these are the stresses caused by bending, so this would be M dy over I, this would be M cy over I. And again, I don't mind about the negative of the equation in this case, because I don't even know if delta H is going that direction or the other direction. So minus both integrals with respect to the area, or area integrals, and these are going to be constant. Whatever C's and D's I choose, the moment is not going to change, the inertia is not going to change. So what I can do from this is MD over minus MC over I, and they're going to be factors of YDA and integral. So times the integral of YDA. And this is not the second moment, because there's not a squared here like with the R and the J or the Y and the I. This is Y to the 1, and this is called the first, not the second, the first moment of area that we just label Q. So this would be a delta M from D to C over I times Q. We'll work with the Q in just a second. That would give me the force. That would give me this force right here, that if I divide by this shaded area would give me the stress. So we'll do that in just a second. One more thing is that if I divide delta H over delta, we'll do that in a minute. So the other thing that we know from the shearing and bending stresses, V and M, is that, for example, if I have a reaction force here and then a load and a cantilever or whatever, this information is the slope of M, right? So basically, if this is 3, this would have a slope of 3, and I don't know, there would be probably a reaction that brings this back down to 0. But again, not just because of this, obviously the reason is from the mechanics itself, but just this example is just to remind you that the V would give me the slope of M. So the slope of M, right, the M dx, the slope in the x direction of M would be V, right? And so basically that's what we're going to do here. My delta H is delta M over delta X times delta X. So I'm not doing anything, I'm just dividing and multiplying by delta X over I. And if this is small enough, this is not just a delta M between C and D, but it's super small, this would just be dm dx, which I just said is a V, the shearing. the shearing force, the shearing load at that point. So delta x q over I. Okay, so V times delta x times q over I. That would be the force. Now I don't want the force, I want the stress. I want the stress. That force is affecting this shaded region, and that shaded area would be equal to what? Would be equal to my delta x, right? That I just defined and used for turning this delta m to a v. Delta x times this length, which is what we define as. So I'm gonna move this a little bit here, which is what we define as t. Okay, that thickness at a specific distance from the neutral axis going up. So for a shear force going down, shear force V going down or going up, the t has to be perpendicular. Why? Because of this, because of what we're doing right now. So that shaded area would be delta x times t. Delta x, just a small distance in the x direction, times this length, which would be the thickness, the width at a specific value of y from the neutral axis. Okay, and that's why t is that value, and that's why t has to be perpendicular to the shearing forces. Okay, so I'm going to use that area because I know that my shearing is that force delta h that I just found over that shaded area. Okay, this load over area would give me the shearing force. My delta h is this value here, v delta x times q over I, and my shaded area is delta x times t. Delta x times t. So the deltas, delta x and delta x, go away, and that is how I end up with shear equal to vq over it, where t is this width. So if I'm at the neutral axis, t would be this, because that's what would give me that shaded area on which delta h is affecting it, and q is the first moment of area. Okay, so this is the last one that we needed to complete our four main types of stresses. I'll write them down one more time. Sigma p over a, but also from bending minus my over I, shearing from torsion tc over j, and the shearing that we just did vq over it. Okay, now the q, which is the other thing that confuses some people, came from this. So I called it here the first moment of area, and it's basically the integral from up y dA, but for this small element. So my y's are only going to go from here, from the shaded area to the top. Shaded area here is here, so it's basically the bottom side of this square to the top. So when I do that integral, it's going to be from here to the top, and that's why q, which is this first moment of area, we do it from wherever we're standing, where the t is, and to the top, basically, of that section of the beam that I took out to do the analysis. Okay, so t, the width, and q from that width, from that location of y to the top. Okay, because it comes from this integral, y dA. And so obviously we could do the integral like I did the I and the j, but instead of doing the integral, we already know, or like in general, we know that the q is going to be the area that I just explained on top of wherever I'm standing, of the t width that I identified, times the centroid, and this is the distance from the neutral axis to the centroid of that shaded area. Okay, so distance to the centroid of shaded area. Right? So like in my example, My neutral axis is probably going to be on the bottom half because there's more area, and I wanted to find the shearing stress right here at some y above the neutral axis. So this is neutral axis. My shaded area for Q, not the shaded area where delta H is affected, like I said before. So not this shaded area, but just the area that I need for calculating the first moment of area. Okay, so basically this for the Q times not just the centroid to the bottom where I'm standing, from the centroid of the neutral of the shaded area to my absolute point of reference, which is the neutral axis. Okay, so this would be the y bar, and this shaded area would be the area that goes here. Okay, so that might also clarify a lot to many of you. So just to end this video with some of the examples that I've been solving in class. If I have a shaft, a rod, or whatever, and I'm trying to find where the maximum stresses occur, when I say we're here at the top, we say that the shearing stress, this one, is 0 because Q is 0, right? So sure, if I'm standing here, what would delta H be? It's nothing, because I'm at the surface, right? If there's a load in this direction, there would be tension from the bending, so there is going to be a sigma equals to minus my over I. There's nothing that's going to be VQ over IT because Q would be 0. Okay. Now where is that maximum? At the center. So again, if I just did a cut, so I take a delta X in this direction, and right here at the center, right where my neutral axis is, this would look something like this. Where this would be my shaded area for the derivation of the equation. Okay, and sure, there is going to be a delta H there, and my Q is going to be from that section that I took out. Okay, so I'm going to have a centroid. That's my neutral axis. The distance to the centroid from the neutral axis is what I'm going to label y bar. The shaded area is going to be this for my Q. So shaded times 1 bar, which is the centroid, and this is going to go here. Okay, so at the top there's nothing because Q is 0, but here at the neutral axis I would have a shearing stress equal to V, whatever the V is, times Q, that I calculate exactly like this, over I, and the last thing, this we're going to end, is the T. Where did that T come from? From this shaded area that is acting on which delta H is acting on. Okay, so delta X times T, which is just in this case the diameter. All right, so that's why we use this T, this distance. That's what we call T, and that's why T is always perpendicular to the force. Okay, so basically, if I didn't have this force going in the minus y direction, x, but if I had a rod and then there's a force in this direction, I would do the same thing, but my cut would come from here. Okay, and then my neutral axis is this, and then this would be T, and this my shaded area for Q. And then the distance from this neutral axis to the centroid of that shaded area is what I would use for Q. Okay, these two have to be perpendicular because of how we derive these equations. Okay.